going to talk about the concept of molecular polarity. And in order to talk about this, we need to remember the idea of a polar and nonpolar bond that we discussed earlier in this chapter. And you're going to need to remember how to determine those polar and nonpolar bonds using electronegativity. If you have a molecule like HF where there's one bond, which is the bond between H and F, you can calculate the difference in electronegativity between those two elements. In this case, 4.0 minus 2.1, you get a 1.9 delta En, or difference in electronegativity, and that means this bond is polar, okay? Whereas if you have a molecule like H2, in this case, you have electronegativities of 2.1 each. Subtract the two of them, you get delta En of 0, which means the bond itself is polar. And of course, we have requirements where up to 0.4 delta En, bond is considered nonpolar, and then greater than 0.5, it's going to be considered polar. Now, if you only have one bond in your molecule, then a polar bond automatically also means a polar molecule, whereas a nonpolar bond also means a nonpolar molecule. The problem is when you have multiple bonds, this becomes a little bit more difficult. To determine the polarity of the entire molecule, you're going to have to calculate something called the dipole moment of the molecule. And that is given the symbol mu, which is illustrated right here. Now, you don't need to know how to calculate either one of these things, but just to kind of give you some information about mu, the unit of it is called debye. The concept of dipole moment is important for us because it tells us how to determine the polarity of the molecule. Now, what we can do is we can measure a dipole moment in an instrument like this where there's an electric field. So if the molecule has some kind of a dipole moment, then when you turn on that electric field, the molecule will line up. The negative side of the molecule will line up on the positive plate of that electric field, and then the positive side of the molecule will line up on the negative plate of the electric. If it's a nonpolar molecule, then when you turn on the field, it would just be randomly oriented like this. Okay, so it's not going to line up like a polar molecule. So how do we know whether something is polar or nonpolar? Based on its dipole moment. If the mu is 0, that means the molecule is nonpolar, and if the mu is greater than 0, then that means they will be polar. Now, the larger the mu, or the more polar the molecule. Okay, we can actually calculate the dipole moment of a molecule using the bond polarity. The way we do that is we would add what we call the bond vector. A bond vector or a bond dipole, it's basically just the length of the line that connects these two bonds right here. And the more polar the bond, the longer that line. And that line is drawn like an arrow, like this. These numbers are just made up here, but if you have an electronegativity difference of, let's say, 0.5, your arrow might be this long. And let's say if your difference of electronegativity is 1.0, the line might be doubly as long. Okay, so you would draw it that way. And then the arrow head is pointing towards the more electronegative element. So like in the case of HF, for example, we would draw an arrow from H to F. So the F is where the arrowhead is. And the length of that arrow would correspond to the difference in electronegativity. These arrows are what we call bond dipoles, and they are vector quantities. So vector is a concept in math. It basically represents a quantity that has some magnitude, but it also has a direction. And the reason it's a good representation of a bond vector is because a bond vector has a magnitude, which is corresponding to the difference in the electronegativity values of the two elements, as well as a direction, right? It's pointing towards the more electronegative element. So in this case, it's pointing that way, okay? So how do we use this idea of a vector to calculate the dipole moment? The way we do it is we would represent all the bonds in a molecule as these bond vectors, and then we would add them up. Now, adding vectors is not as simple as just adding regular numbers. You have to consider both the number, which is the magnitude of the vector, as well as the position of the vector, or which way it's pointing. So for example, if I have two bonds that are both pointing that way, which is from left to right in this case, so I add those two vectors, then I'm going to get a vector that is twice as long, because it's 5 plus 5, so it becomes 10. So it's a vector that's pointing from left to right, but then the length now is 10. However, if I have a bond that's pointing from left to right in one case, and then I have another one that's pointing from right to left, and they have exactly the same magnitude, which is 5 and 5, the one that's pointing the other way would be considered -5. So when I add these two together, I actually get a result of 0. So earlier I would get a dipole moment that's really big, whereas now I would get a dipole moment that's equal to 0, which of course means I have a nonpolar molecule. Okay, now there are other informations here about how to add vector, but key thing to remember is you are not required to add vectors in this class. So that's the good news. However, what you should do is you should understand how the dipole moment that we get in different molecules and how to use that information to predict the polarity of a molecule. Okay, so let me just give you some examples here to kind of illustrate how these vectors are added up, and then later on I'll give you some simple rules that you can use without knowing anything about vectors to be able to determine the polarity of a molecule. Okay, so let's start with CO2 here. So we always have to start with Lewis structure with determining polarity. Once you draw the Lewis structure, you need to draw those bond dipoles. So the bond dipoles, again, is drawn from the less electronegative element to the more electronegative element. In this case, oxygen is more electronegative, so we're drawing the vector from carbon to oxygen. The arrowhead ends in oxygen, and it has a certain length. That length corresponds to the delta En of the CO bond. And then the other CO bond also can be represented by another bond dipole. In this case, it's pointing from left to right. The length is the same. So in other words, we have two bond dipoles. They're pointing opposite direction, and now we have to add them to figure out what the dipole moment of carbon dioxide. And as we talked about earlier, if you have two vectors that are opposite from each other, in this particular case, they're pointing, away from each other. It's the same idea. One of them has a length of 1 because that's the delta En. The other one would have a length of negative because it's pointing the other way. So when you add the two of them together, you get a 0 dipole, which means carbon dioxide is a nonpolar molecule because its dipole moment is 0 Debye. Okay, and so that gives you some idea how we do this, right? Let's take a look at water. So water, this is the Lewis structure, right? HOH, O is in the middle. Now, which way does these bond dipole vectors point towards? Well, they point to oxygen from hydrogen, right? Because oxygen is more electronegative than hydrogen. Again, you can look at the value of electronegativity between hydrogen and oxygen right here. Okay, so we know that the arrows are pointing towards oxygen. There's a certain length to them because they both have that same delta En. And how would you add these two type of vectors? Well, when you add these two, you have to add them using a vector addition, which is to put first this arrow and then you put the second arrow. The beginning of the second arrow should be placed at the end of the first arrow, and then you draw the resulting vector is the arrow that you draw from the very beginning of the first arrow to the end of that second, and then turns out to give this longer arrow, which is a longer vector as a result. But the bottom line there being that the dipole moment in this case is not 0, right? Because when you add it, you get a much longer vector. So since the dipole moment is not 0, water is polar. So we just had two examples where in one case we have polar bonds, the CO bond is polar, but the molecule is non-polar. Here we have a second example where the bonds are polar and the molecule is also polar. So very important to understand that even though you have polar bonds, it doesn't mean that you're always going to have a polar molecule. Sometimes you can have a non-polar molecule. It depends on how these vectors add up. Okay, now another example that we can look at is CCl4 and CHCl3. So these two molecules look the same in terms of its Vesper shape. They're both tetrahedral, but what I did here is just replace one of the chlorine atoms with H. Okay, so that makes it two different molecules. So this one is what we call carbon tetrachloride. This one is what we call chlorophyll. Well, it turns out that carbon tetrachloride is actually nonpolar. Why is it nonpolar? Because when you work out all these bond vectors, there's 4 of them here. When you add all of them up, they end up giving you a dipole moment of 0. Whereas with this one right here, when you add all 4 of them, because the H is a different length vector from the other 3, when you add all of them up together, they don't add up to 0. It's slightly above 0. So this molecule is actually polar, okay? Whereas that molecule is non-polar. So again, even though they look exactly the same, just changing one atom is enough to make one molecule non-polar and one molecule polar, okay? So why does this matter to us? Because it actually affects how the molecule can interact with other molecules. It affects how the properties of the molecule can change as a result of that polarity. Just to give you a quick example here of two things that look pretty much the same except of the polarity. Okay, these are what we call isomers, something you learn a little bit more about in organic chemistry. This molecule has the same formula. So if you count the atoms here, there's 2 carbons, there's 2 hydrogens, and there's 2 chlorines. Same with this one right here, right? You see 2 carbons, 2 hydrogens, and 2 chlorine. So the formula is the same for both of the molecules, but the arrangement of the atoms is slightly different. In this one right here, the H is opposite from one another from that double bond, and the chlorine is also opposite from each other across that double bond plane. And then with this one right here, the chlorines are on the same side of the double bond, whereas the hydrogen is on the other side of it, but it's also on the same side, okay, compared to this one. Interestingly, if you add up all the bond vectors in this molecule, you get a mu of 0, which means this molecule right here, the one on the left, is nonpolar, and then this molecule right here on the right, when you add the bond dipoles together, you actually get a 1.9 divide, and so that molecule is actually polar. Well, it turns out that if you actually try to boil these two molecules, one of them boils at about 48 degrees Celsius, and the other one boils at 60 degrees Celsius. Okay, so quite a bit of a difference just because of the polarity, okay? That it actually changes the way the molecule behaves just because of this little simple difference in their property. All right, now we're going to talk a little bit about how you can determine polarity if you don't know how to add vectors, right? Because you don't need to know how to do that in this class. Well, you can just follow these simple rules. So I have made these rules to help you determine polarity of pretty much most of the molecules you'll see. This will really cover a huge amount of molecules that you will encounter, particularly in general chemistry. Okay, so what are these rules? First off, if all the bonds that you see are nonpolar, automatically your molecule will be so don't even have to think about it. If you have at least some bonds that are polar, then you have to go through these ABC right here to see where you land, okay? So if some of the bonds are polar, first you have to check, does the central atom have lone pair or not? Okay, so for central atom with no lone pair, and then identical terminal atom, the molecule is nonpolar. And we're gonna do an example on this so you can see how this is being applied, okay? And then if your central atom has no lone pair, but then you have different terminal atoms, then your molecule is going to be polar. Now, if your central atom have lone pair and your molecular shape, which you determine through VSEPR, is either linear or square planar, then your molecule is nonpolar. Otherwise, your molecule is going to be polar, okay? All right, let's talk about how to determine the polarity of these 4 species. So the first step is always to draw the Lewis structure of all the molecules. I assume at this point everybody's comfortable doing that, so I just drew out the Lewis structures of the 4 species that's shown there, okay? And then I attach here the rules that I just described to you on how to determine polarity. So we're going to apply that. So first, we're going to need to look at NH3. So with NH3, we have to determine first whether the molecule is polar or nonpolar using the bonds. So the first step is just figure out the bonds. Now, for the bonds, you're going to need your electronegativity values. And this, you're going to need to look up that table that has the electronegativity values of each of these elements. So I'll just write down here that nitrogen is 3 and hydrogen is 2.1. The difference between those is 0.9, so 0.9 is big enough that the bond itself is polar. Okay, so if the bond is polar, you're going to have to look at number 2 here, where we're talking about polar bonds, right? The question is, does the central atom, which is nitrogen in this case, have a lone pair or not? Now, it has lone pair, and then so we have to see what is the molecular shape. Is it linear or is it square planar? If it's not either one of them, then it's going to be polar right away. Well, we look at NH3, the molecular shape is actually trigonal pyramidal, right? Because it's a tetrahedral electron geometry, but only 3 bonding pairs here. Since it's not linear or square planar, then NH3 would be polar. So I'm going to write here next to NH3, polar. Okay, let's take a look at our second one, which is BF3. Almost look the same like NH3. Has 3 bonds, but no lone pair on the central atom. Okay, well, first thing is to look up the BF3 to see what kind of bonds we have. So B itself has an electronegativity of 2.0, and then F has an electronegativity of 4.0. So that bond is really pretty polar. See in this case that there's no lone pair in the central atom. Then we have to see if the terminal atoms are identical or not. Okay, so if there's no lone pair, there's 2 options here. Identical or different terminal atoms. Well, the terminal atoms are all F, so it's identical terminal atom. So that means the molecule must be nonpolar. COS, the formula is written as COS, but when we draw the Lewis structure, C has to be in the middle. Let's figure out what that one is. In this case, our bond dipole, we have to determine electronegativity. So carbon is 2.5, oxygen is 3.5, and sulfur is 2.5. So here you have one bond that is nonpolar, and then another bond that's polar. Okay, the CO bond is polar. Now, in the rule, as long as you have even one polar bond, you're going to have to go with the bonds are polar rule. Okay, so in this case, since we have one bond that's polar, we're going to go with that one. Do we have lone pairs or not in the central atom? Well, we don't, as the C doesn't have any lone pairs, so that means we got to choose one of these, A or B. Do we have identical terminal atoms or different terminal atoms? Well, terminal atoms are different in this case. Since it's different, molecule is going to be polar. Okay, last one, XeF4. We first figure out the polarity of the bond. Xe, it is 2.6, and then F is 4.0, so the difference is big enough to make it a polar bond, all four of them. Since it's a polar bond, again, we're going to number 2 here. Do we have lone pairs or not on the central atom? We do. Since we have lone pairs, that means we're going to go to part C. Is the molecular shape here linear or square planar? Well, let's check, right? This has 6 pairs of electrons around the central atom, which means it's an octahedral geometry, electron geometry. What about the molecular geometry or the molecular shape? Well, 4 of those are bonding, and 2 of them are lone pairs. So when you have 4 plus 2 like that, that gives you a square planar shape. Okay, so square planar means that it's nonpolar. So even though it has a polar bond, it has some lone pairs around it, it's actually a non-polar molecule. So hopefully those examples help you in determining polarity of molecules.